This is the first video for Unit 2, Lesson 1, Rates of Change and the Tangent Line Problem. This unit is about differentiation, the definition, and some basic derivative rules. So we're going to circle this around again to where we started in Lesson 1 of Unit 1 with average and instantaneous rates of change and how we connect that to where the derivative comes from. Okay. So some terms that we use a lot, one of which is secant line, which you guys talked about in geometry. And in geometry, you said it intersects a circle or a curve in two places. And tangent line would only intersect a circle at one point. So when we're studying calculus, though, this has to be defined a little differently. So when we're talking about the tangent line and we're drawing it on a curve, it has to be intersect the curve. We're talking that it's going to intersect it in more than one place, but we're only talking about a specific point. So for instance, the red line in this picture here shows a tangent line that looks like it should be a secant line, but it is a tangent line because we're looking at the behavior right at point P here. It's actually not even that far. I can cut this down a little, like right here. So the idea is now the tangent line to a curve at a point is a line that best models the behavior of the curve at that point. So even though it touches over at Q, what we see here is the direction of that red line and the curve do not have anything in common. But at P, that little section right there, it models the behavior of the curve. So that's why we would say the line y equals g of x is tangent to the curve at P. The reason why we want to know that is that we want to find the slope of the curve at a point. This slope of the tangent line, which is also slope of the curve, is our instantaneous rate of change, also called the derivative that we've been talking about. So the most important thing is that a tangent to the curve at any point is unique, and that is very important. It is definitely unique because you're going to move that as you change your A in this picture. If you were to move your A up the curve further to like there, I can make a little dot, your tangent line would then be up further like that. So it would have a different slope and it would have different characteristics because of that. You can also have tangent lines that change direction as you move it along the curve. So at one point, a tangent line could have a positive slope, at another point, it could have a negative slope. So the important things to note here is that a function that is defined has a defined slope at x equal a has two things in common with its tangent line. It's two things in common with its tangent at x equals a. One is the point of tangency. It has to touch somewhere. So let me take this off now. It has to touch somewhere, and it touches at a f of a. The slope at the point of tangency denoted by, we say, f prime of a. F prime of a. That's how we say that, f prime of a. F prime of a. Okay, so that's the slope at the point of tangency is read f prime of a, and it's also the slope of that tangent line. Any function with a defined slope at a specific point will have one and only one tangent line at that point. It is unique, and that is important because it helps us define the characteristics of the function. Okay, so taking a step back, let's talk about the secant line and how it gives us average rates of change. So it's going to join any 2 points on a function. So the slope of that secant line through the point, so in the picture we have point P, which we're given coordinates a, f of a, and point Q, which we're given coordinates b, f of b. We can find the slope of that red line. Okay, so again, we have the change in y over the change in x, which is our average rate of change. is the slope of the secant line. So we have f of b minus f of a over b minus a, which is a little different than our old notation back in the day, which was y2 minus y1 over x2 minus x1. We want to be a little more precise about how we talk about it because we're relating it to specific points on a function. So let's do the first example. It says, find the average rate of change of f of x equal to x cubed minus 3x. And how we do that is over the interval 1, 3. You need to have the interval. So we need to know what f of 3 is, and we need to know what f of 1 is. Now you can do them separately or you can do it right in the fraction. It's up to you. I'm going to do them separately here. So 3 cubed minus 3 times 3 gives me 27 minus 9, which gives me 18. F of 1 is going to be 1 cubed minus 3 times 1, which is going to be 1 minus 3, which is negative 2. So now I can do my average rate of change, which is going to equal 18 plus 2 over 3 minus 1. And then so I get 20 over 2. So my average rate of change is going to equal 10. Okay, that's how you do that. It's just like you did in Algebra 1 or Algebra 2. Okay, so now going back to our instantaneous rate of change in our tangent lines, find the slope of a tangent line will give us an instantaneous rate of change, but the problem is we only have a single point to work with. So what we have to do is kind of take a point that's a little further, because otherwise we get this indeterminate form. So that's what our plan B is. We choose a point that's very, very close, excuse me, to our point of tangency, and we call it point Q. So let's take a look at the second picture here. So point Q is so very, very close. And in this picture, it looks a little far away. And we can algebraically estimate the slope of our tangent line and then just move that amount away. And we usually use the letter H for that movement, that little distance away. So 2 points in the average rate of change in formula, the slope of the secant line. If we move point Q down towards where A is this way, we move it down. And so our H is moving in here. So it's almost on top of A. What we're going to end up doing is H will go to 0 when Q is directly on top of P. So that's going to be our old friend, the limits, coming up here. So we're supposed to use the 2 points P and Q in the average rate of change formula to find the slope of the secant line. Okay, if we move point Q directly on top of point P when H goes to 0. So what we're going to get here is what's known as our difference quotient. So our average rate of change is going to be our f of A plus H minus our f of A. So that's our y value at Q minus our y value at P over A plus H minus A. So this simplifies to f of A plus H minus f of A all over H, because the A's will cancel. So this is our difference quotient. And I've been trying to get you guys ready for this. You saw some in Chapter 1. Those of you who had me last year saw this in Chapter 11, our difference quotients. So we're going to be formalizing it for everybody here. Okay. So although the slope of a curve is always changing, we know the slope of any line is constant. Even our tangent line, it's a line, so it has a constant rate of change. So we're going to use our limit rules to our rate of change. So as H approaches 0, we can use algebraic techniques and then evaluate the limit to find the slope. So here's our official definition of the slope of a curve at a point right here. So y equals the curve f of x at a point P f of A. I'm sorry, point P, A, f of A is the number m. So we have the limit as h approaches 0 of f of A plus h minus f of A over h. And And the provision is provided the limit exists, because we are going to have points on the curve where the limit does not exist, and that's very possible. So this is, of course, our difference quotients, our f of a plus h minus f of a over h. So using algebra, our goal will be to simplify this quotient, then evaluate the limit as h goes to 0. And you should get a number value if you divide out the h in the denominator. And I've mentioned this before, but it is true. If the derivative does exist, the slope of the tangent line, the h's will indeed cancel out, so you can find the limit. So let's do some examples of the difference quotient. So we're supposed to find f of a and f of h for these. And then in the next the next example, we'll actually use the difference quotient. So this is just getting you used to how this should look. Okay, so f of a is just going to be a substitution of x for a, so you get 1 over 2a. And f of a plus h is going to equal 1 over 2 times a plus h. And if you simplify that, you get 1 over 2a plus 2h. b, f of a is going to be the square root of 3a minus 2, and f of a plus h will equal the square root of 3 times a plus h minus 2. So we get f of a plus h equals the square root of 3a plus 3h minus 2. I'm going to leave letter C for you to do, and I am going to do letter D. So f of a is going to be 3 over a plus 1, and f of a plus h is going to be 3 over a plus h plus 1. Okay, so pause the video and take a second to do letter C, and I'll put the answer on in a second. Okay, so there are the 2 answers for letter C. If you have questions, you can ask me in class tomorrow. Okay, so I'm going to finish the first part of this by doing number 4. So we're going to go through the whole thing. So we're asked here, given the function y equals f of x, use the difference quotient to find the slope of the curve at the point 3, 9. So with that point, here's what we know. We know that our a equals 3 and our f of a equals 9. That's what we know. So we're going to find the slope using our difference quotient and the limit as h approaches 0. So we're using f of a plus h minus f of a all over h. So we're going to substitute in a plus h for x squared. So we're going to have the limit as h approaches 0 of a plus h squared minus, and we can just substitute in 9 for f of a because that was given to us, all over h. Now we're going to expand that, so we get the limit as h approaches 0 of a squared plus 2ah plus h squared minus 9 all over h. Oh, I forgot to put, I'm sorry. This should be a 9, because, I'm sorry, a 3, because we know that a is 3. So that's a little correction here. So this should be 3 plus h. So this number should be 9, which is 3 squared. And what told me that was I realized the 9 wasn't going to cancel. So the 9's cancel. So I'm left with the limit as h approaches 0 of 2. I'm sorry. Let me go back here. Let me redo this. I apologize. Let me redo this whole line. Okay, so this is going to be 9 plus 6h plus h squared minus 9, because I didn't substitute the 3 everywhere. I apologize for that. All over h. So when we simplify this, the 9's cancel, and we're left with 6h plus h squared all over h. So this is why it's important to have everything that doesn't have an h go away, because we want to be able to take the limit. So we're left with the limit as h approaches 0 of 6 plus h. So this is a simple function that we can substitute. So we get that the slope of the tangent line of the curve at the point 39 is 6. I'm going to continue our discussion of tangent lines in the next video.